Thank you very much for the kind invitation. It's a real pleasure to be in this wonderful place and in this wonderful conference. I've been working for several years in network theory. Network theory is one of the most prosperous fields in science. It is an interdisciplinary field. And the goal is to understand the underlying topology of dataset of interacting system, which takes the form of a network. And this can be in social science, in technology, or even in biology. But recently, there is a recent interest in developing and hope that developing a network topology and geometry could be relevant for a variety of applications ranging from brain research to routing protocol in the internet. And so the research is taking some momentum and to some extent, some of the algorithms that have been proposed use a Clique complex. So starting from a network, they extract the simplicial complex by considering the Clique complex. And one of the most important algorithms that has been developed, probably even before understanding that this was actually a Clique complex, is this algorithm called Clique percolation, in which one considers a clique, for instance, a 4 clique, and then roll a clique, meaning that consider all the cliques that have one new node and that share k-1 node with an existing clique. In this way, the cliques can be rolled and one can find mesoscale structure or community structure in the network, and this algorithm can find overlapping community, so some node can belong to different community at the same time in this way. And there is a nice application to collaboration networks or to this wonderful data set of word association network, where people have been given a set of words and they had to write down words that they believed were connected, and the network that result, for example, here you have the network of the word bright, result in different community that have different meaning. You can associate with word indicating intelligent, light, astronomical concept, and colors. And yes, so another approach, is more recent approach, is aim at developing some homological scaffold for network by starting with weighted network and inducing a filtration by cutting, considering all the links which have a weight larger than a given threshold, and then constructing a Clique complex out of it. And in this way, it was found that actually from some brain functional network, it was possible to infer some significant differences that were not observed by more standard network theory approach. There is another set of question and data sets that can be studied with simplicial complexes, and traditionally they take the form of a simplicial complex, and people have done this exercise of just extracting the one skeleton out of it, but actually the real data set is a simplicial complex, and we can extract more information if we look at this in this way. And for instance, this was already cited by Dima Tukov in his paper here of Tadusty. And here you have 3 regions of the brain that you can have, that they can be, you want to distinguish between the scenario in which they're correlated pairwise or they're activated at the same time. And you would distinguish this different behavior just by considering them as a triangle formed by just 3 links or by 2 simplex. formed by a field triangle. Another data set which takes the form of a simplicial complex is in the cell protein. They bind together to find protein complexes, and these protein complexes perform a function in the cell. And so these protein complexes are really simplices, and it's a joke in wording, complexes using with two different meanings, but these are simplices, and actually the network is a simplicial complex because a protein can belong to different complexes at the same time. But usually people look at this data just from the pairwise interaction perspective. In collaboration network, we have many data sets which takes the form of a simplicial complex. So, for instance, a moving can be co-acted by several actors, or a paper in general, for instance, in biology, this standard can be authored by more than two authors and forming a simplex. And so simplices are also important because the hope is that by studying simplicial complex, one can reveal the hidden geometry of network. And this is an idea that has been put forward by Dima Kryukov and Marianne Bourguignat, is that actually a network might have a hidden geometry, so that two nodes that are connected in the network are actually close in space in this hidden geometry. And the question is, what is actually what is the characteristic of this hidden geometry? And actually, there are different results which point at the fact that actually an hyperbolic geometry could be important for having efficient greedy routing in the internet, where the packets are sent according to the hyperbolic distance between the nodes in the internet, and not just by routing table. And there are different idea, and in particular there is always by Dima and Marianne, there is a model which generates complex network geometry similar to the internet, for instance, in which nodes are sprinkled into a Poincaré disk, and then links are established according to the hyperbolic distance between the nodes. And this yields this network which have several properties similar to the real internet dataset. But here what I want to tell you is some research aim at defining some emergent geometry. So aiming at considering a model which generates network with hidden geometry using rules, dynamical rules, or equilibrium or non-equilibrium, that do not explicitly take into account an embedding space. So just by having a purely combinatorial rule, you want to generate networks that have some geometrical character, or can be characterized by some hidden geometry. And this is an idea which is relevant for a variety of applications, because this idea of hidden geometry is this. So the internet, there is no really embedding space of the router in the internet, or things like this, but actually is an idea that is borrowed by the field of quantum gravity, when this is a problem at the heart of the field, in which you want to explain how the fabric of space-time emerge. And actually several several approaches to quantum gravity use a discretization of space-time, and these include causal dynamical triangulation, tensor network, quantum field theory, and quantum group field theory, and causal set, and so on. So here, not all these approaches really believe that the fabric of space-time is really discrete at the macroscopic level. Some just use it as an approximation to the continuous, but the technique of network and simplicial complexes have been used in quite a number of these approaches. So let me go back to network theory and tell you a bit of the background information, and then I will present you a model of emergent geometry, and this will be a non-equilibrium model. So we have heard yesterday Dima speaking about equilibrium model of network. I also spoke about it in the school, but this will be just of non-equilibrium growth of simplicial complexes. So complex networks describe the underlying structure, topology of biological, social, and technological system, from protein interaction network to the internet. And they live in a wide space between very regular structure and completely random graph. So although here this space is quite big, as a real network have been shown to display some universality property, some property that are shared by many real data sets. And these include the small world property, and this is very nice to speak about it here, because this is about actually the Hausdorff dimension of the graph, which is infinite. So this the diameter scale like the logarithm of the number of nodes, a bit like in a Cayley tree or in a beta lattice. And another property is the scale-free networks, meaning that the degree distribution is quite broad. And another one is that many networks share communities or regions of the graph that are more densely connected than others. And the scale-free property regards the distribution of the number of links of each node, and this takes the form of a power law for large k, for large degree, where this exponent is between 2 and 3 included, meaning that the average degree is finite, but the second moment diverge, meaning that if you take the double of a size of a social network, then average number of friends remains the same, but the fluctuation diverge, meaning that the average is not characteristic of the network, and the system is dominated by up. And there is a wide class of networks which share this property, and you see this is a map of the internet. They have this very significant up node of many connections. And these properties find quite ubiquitously in a variety of different systems. And actually, we are now familiar with this scenario, but this is actually puzzling. Why do we observe this universality in many networks? So one of the answers that is one of the most successful answer to this thing is this property, is that actually there is some basic mechanism, universal mechanism by which this network grow, and that is based on growth. So if you look at the internet, at each time the number of the World Wide Web, the web page increase, the number of papers in a citation network increase. So you start with a finite network, and at each time you add one node with m links, for instance 2 links. And then there is a second ingredient, which is a prescription of how these links are put, which is the preferential attachment, so that nodes which have high number of connections are more likely to acquire new links. and this kernel is linear in the degree, and these two ingredients just give a scale-free graph with an exponent -3, so in the region of interest between 2 and 3. So the story goes that what we teach us the courses is that if you have instead growth, but you don't have this preferential attachment, then the network is exponential, so you don't have this property that the second moment of the degree distribution diverge, and this it is in another universality class. It's not in the universality class that we observe in a number of data set. So the story goes that we always say we need preferential attachment in growing network model to generate scale-free network. So let me just tell you a bit, a kind of a comment on these dynamics, and relating these dynamics to some property that map this graph to quantum statistics. So in this model, the BA model can be seen as the addition to the network of a unitary cell, a bit like in a lattice. You have one node and 3 links, M links, and you might think that there are 2 possible ways to attach this unitary cell to a network. One way in which it is the BA model, in which you have one new node that is attached to M old nodes, and the inverse, in which you have one of node which gives rise to 3 offsprings, new nodes. And so additionally, we want to put some additional ingredient in this model, and we want to assign a quality, an intrinsic quality to the nodes, which is modeled by a quantity that is called energy, that is drawn at each time for each node from a G epsilon distribution, and then it's remaining there, quenched variable, doesn't change in time. And from this energy, we consider a fitness, which is a quantity which is associated to a node, and which takes this exponential form. So when beta is equal to 0, the fitness is 1 for each node. When beta is very big, the fitness of node with low energy is I, much higher than the one with high energy. So we can have a BA model in which we attach this unitary cell, one new node and M links, and we attach that with preferential attachment, so to web pages that are very popular, but also to web pages which are very fit, meaning that have a high interesting content. And we model this by this modification of the kernel. So we can build a kind of, here I'm not sure how to call this, a reverse dynamics, in which instead there is a one old node which grows and giving rise to M new nodes. So we assign a variable rho I equal to 1 to every node that has not already grown, and rho I equal to 0 to a node that is in the bulk of this tree. And we define this algorithm that then generates a Cayley tree. So in this way, I was looking for some algorithm to find some opposite or symmetric, kind of symmetric dynamics of the two networks. So this model can be studied with the master equation approach, which gives exact result, but a lot of insight can also be gained by the mean field approach, in which one studies the average degree of one node as a function of time. And the equation for this mean field approach looks quite similar, and they they are related by a time reversal and because M can be absorbed by a rescaling of time. So now I want to tell you how this from these dynamics we find that these graphs are described by quantum statistics. So in physics, you have classical particle which can be in different energy states, and they have occupation number between 0 and infinity, and they follow a Boltzmann statistics. But in a quantum world, the particles are really distinguished between Fermi particle and Bose particle. And the Fermi particle have the satisfied exclusion process, so any energy level can be occupied by 0 or 1 particle. The Bose particle instead do not have an exclusion rule. And the average of this occupation follows this quantum statistics, classical and quantum statistics as a function of S. And mu here is a chemical potential which is fixed by the conservation of the number of particles in the gas. So here, when we solve the FES model, the Bianconi-Barabasi model, we see that actually we can construct a self-consistent solution to the model in which the average degree of each particle increases in time as a function of the fitment and as a function of a self-consistent constant, which is fixed by the same equation that fixes the chemical potential in a Bose gas. And actually, this graph can be mapped to a Bose gas. And similarly, for the other dynamics of the Cayley tree, we have a the dynamics described by self-consistent constant, which is fixed by a self-consistent equation which fixes the chemical potential of a Fermi gas. So in a Bose gas, we know that there is a phase transition, so the Bose-Einstein condensation, as a function of this parameter beta. And in the network, simultaneously, we see that there is an important phase transition in which one node grabs a finite fraction of all the links. This is a structural phase transition that can be predicted by the solution of the model. And in a growing Cayley tree, the energy of the node in the surface of the tree, so the tree grows like this, and then the energy on the surface follows this Fermi distribution. So let's go back to simplicial complexes and see how these insights can help us understanding how this growing network model behave when one looks at growing model in which we grow by adding triangle, tetrahedra, and we will also always consider pure simplicial complexes. So we will define a generalized degree of every phase of a simplicial complex. So we will consider pure simplicial complex of dimension D, and we will associate a generalized degree of each phase given by the number of D simplices incident to the phase. So for instance, here you have link 1 and 3, which are incident to 3 to simplex, and node 3, which is incident to 4 D simplices. This is the generalized degree of the node and link. For the D-1 phase, we associate the generalized degree -1, and we call the incidence number. And actually, when this incidence number is it takes only the value 0 or 1, we are sure that we have a manifold. The simplicial complex is a discrete manifold. So we consider a growing simplicial complex model in which we start with a D simplex, And at each time step, we add a new node, a new D simplex, which has a new node and is connected to a D-1 phase, which is existing in the graph. And when we have to choose the D-1 phases, we choose it with a probability, which depends on a parameter, which is called flavor, which takes the values -1, 0, and 1. So this is the kernel probability. So let's look more closely at this kernel. When S is equal -1, the probability to attach to a D-1 phase is proportional to 1 minus n mu. And so you start with a simplex and a new phase, which is adjacent only to a given simplices, so as an incident number 0, and then you can attach a new D simplices to it, but then it will have a incident number 1, so you cannot attach a D simplices anymore, and you construct a manifold like this. Or you can have a uniform attachment when you attach to any D-1 phase as many times as you like. Or you have 1 minus, when S is equal to 1, you actually attach to phases according to their generalized degree. So you have effectively a preferential attachment dynamic. So in D-1, we have the scenario we are expecting, given that we have studied network. So for preferential attachment, we have the BA model, essentially, the 3 BA model. For uniform attachment, we have an exponential graph. And for the manifold, well, we have a chain, because we can just put links along each other. But in D equal to 2, already with uniform attachment, we get a scale-free graph. This is because we are attaching triangle to link uniformly, so we end up adding a new link to a node preferentially to many links it has already. So there is an emergent preferential attachment, while the manifold is exponential. In D equal to 3, also the manifold becomes scale-free. And actually, this can be explained here. You can consider this 3 tetrahedra incident to a node I. So node I is attached to 5 unsaturated phases where we can still attach simplices. And now we attach a new tetrahedra, and node I is incident to 6 unsaturated phases where we can still attach simplices. So there is, again, a preferential attachment induced by the geometry, by the fact that we are in dimension D equal to 3. And this is actually what happens in any dimension greater than 3. So the generalized degree distribution follow this very regular pattern. And if you look at the manifold, for D-1 phases, bimodal, exponential, and power law. And for S is equal to 1 is exponential, power law, and power law. And for preferential attachment is power law all the way for any dimension. And so actually, these network geometry with flavor are scale-free. We can prove that are scale-free for any dimension greater than 2, so 3 and above. So, sorry, let me. Yes. So if we allow the link to have all equal length, our conjecture is that actually the most natural emergent geometry for this object is hyperbolic, where we start from the triangle in D equal to T, and we attach triangle randomly to every D minus 1 phase. And actually, we can extend this to 3D, and actually we can also look at the position of the node on this boundary of this space, and we can project this in a Euclidean coordinate, azimuth and angle, and we see this pattern arising, and we recognize from this actually the Apollonian network. So the Apollonian network is a network formed by starting from the Apollonian packing, in which at the center of each circle is connected by a link. Each tangent circle are connected by a link. And in this way, you construct this Apollonian network, which is known to be a scale-free network with a given exponent gamma. So here, our construction constructs a random Apollonian graph, because it's not growing in all directions simultaneously, but subsequently. So from this constructor of simplicial complexes, you can project and you can find this Apollonian graph. Let me quick go toward a generalization of these dynamics, putting some energy to the nodes. And actually, we don't also put an energy to the nodes, but also to the links and to the triangle. So how we do that, given that we assign an energy to each node, the energy of the link is the sum of the energy of the two nodes, and the energy of the triangle is the sum of the energy of the three nodes belonging to the triangle. So we can generalize these dynamics just by putting a fitness that depends on the energy of the d-1 phase to which we attach the simplicial complex. And now we are looking at the network, the simplicial complex that result. And so for S-1, so for this manifold, actually we note that our constructor has a dual, which is a 3. So we can, this is quite interesting, because actually for NGF, we observe that as long as beta is not too high, so for an expansion of high temperature, a low beta, we have that the average of the generalized degree follow the Fermi-Dirac, the Boltzmann, and the Bose-Einstein distribution, respectively, for different phases, for triangular phases, for links, and for nodes. So the generalized degree -1 over phases of energy epsilon follow this pattern as long as the temperature is sufficiently high. So what happens to the geometry, so this our geometrical constructor? Well, we start with this, for in d equal to 2, we are at high temperature, so this object grows in all directions more or less uniformly. But if we lower the temperature, so we go to higher value of beta, then there is a breakdown of this self-consistent equation, and actually the simplicial complex apparently, this is only numerically, choose only one direction where to go. And similar happens in d equal to 3, where for a low value of beta, it grows more or less uniformly, but for high value of beta, it apparently chooses one direction. So this, I come to my conclusion. I wanted to tell you about this model, our PET model of simplicial complexes, displaying some emergent geometry. And these are graphs which are interesting from the network's perspective. So I did not mention that, but I also have some community structure with high modularity, finite clustering coefficient. But interesting, they have this emergent scale-free property that depends on the dimension of this object. So network geometry, which are manifold with flavor s minus 1, are scale-free for dimension d greater than 2. For s equal to 0, are scale-free for d greater than 1. And there is this conjecture that actually if the links are equal length, this is a hyperbolic emergent geometry. And when we have a finite temperature, so we include this fitness and this energy, then we have this connection with emergent quantum statistics, and we can see that at high temperature they undergo phase transition, in which they apparently choose one direction where to grow. And this is a list of references. This growing network model have been developed mostly with my collaborator Christophe Ramede. We have some work on a weighted version of this with my student Owen Courtney, and other work on a different approach and ensemble of simplicial complexes. Thank you very much for your attention.
Grow these things in higher dimensional, like adding triangles. Are you always adding a triangle with a new node?
Yes.
What happens if you can attach triangles without adding a new node?
So we have a model. This model here, the VU model, in which we do exactly this. So these are objects always with these that are, I don't know if I have a slide, yeah. So we do this move, and then we do this move. And we can get this kind of graph for the manifold. So we have always a small word graph, so the boundary scales like the volume, but it looks more like a manifold and less like a sphere. So I think this is one generalization. Another one we are doing with my student Owen Courtney is instead of starting with one triangle at each time, we take one node with two triangles. So it's always one new node, but it has two different triangles. So this generates a network with a negative Euler characteristic, because at each time you add some all.
Other questions? Yeah, so I guess I wanted to ask pretty much the same question. So my idea was a slight variation of that. That at each time step you would have some probability of the new D simplex having two of its faces being existing minus one. So
Yeah.
So I like your model. Just if you added that, then not only would you get kind of new geometry, but you get new topology. Topology would be non-trivial, and you could. So I don't know if it would happen in nature, but you could ask interesting mathematical questions. Like eliminate topology. In fact, the persistent homology would change. So what's the persistent homology of this?
Yes. Yes, so I mean, this model that this model here doesn't change the topology, the homology, because it's just always a sphere-like object. But if you add this is why we are exploring this, adding this kind of structure. So here you have your simplicial complex, and you add one node and two triangles. Here you can add, alls and loops, and so. But of course, there is a variety of possibility that you can explore. So this is quite easy to do, and you can generalize the network geometry with flavor with this. Yes, but there is a nice zoology of move that you can think of.
The some of the data sets available somewhere? Different types of networks?
Yes, so there are many data repository. So, for instance, the Stanford one is a standard one, or things like this. For simplicial complexes, is a bit more tricky. So sometimes people just constructed from dataset. For instance, there is the APS dataset, this collaboration network of all the journal of American Physical Society, which you have, but you have to construct the simplex from.
Many social network data sets, brain network data sets, for example.
For the brain network.
It's really difficult job doing something.
Yeah, you should ask him. Yes, I understand this, but things are moving in this context, so there will be probably some people starting to put there some data repository for simplicial complex dataset. So at least for multi-layer network, which is another field in which I'm active, there is a lot of this. So.
Other questions? So I have a question. So you talked about dual graph. I was wondering if there is a duality result. We could find duality results relating the behavior of the dual tree in the case, and the behavior of the one-scaling graph.
Yes, this is interesting. But actually, I think there are different ways to build a dual. If you just build a dual, like every simplex, you put a node, then your dual is not a simplicial complex. It's just, for example, for a manifold, it's just a tree. And there, you lose some information, I guess, because, for instance, these quantum statistics or just this generalized degree distribution, you could not guess from the dual, because in the dual you lose the information of the identity of the d-1 phase. So you have two d-dimensional simplex that are connected by d-1 phase, but you lose the information about the identity of the node there. So, well, I don't know, maybe it's just that I need to study more, but it looks to me that you are losing some information if you are not smart enough.
Okay. No more questions?